Hello and welcome to the next in the series of talks about analog electronics and physics. This time introducing the subject of linearity. Now, there is a very useful and powerful technique in analysing circuits called superposition. And superposition only works for linear circuits. So the point of this first talk is to introduce what I mean by a linear circuit. And we'll start with, what do I mean by linearity? Well, simple definition. Output is linearly related to an input if and only if the output y is a constant times the input x. I don't know if you know about this mathematical term here, IFF. It's not a typo. It stands for if and only if. This condition is both necessary and sufficient for the conclusion. If this is true, then we have a linear relationship between y and x. If this is not true, then we do not have a linear relationship between y and x. We've already seen one such linear relationship, and that is Ohm's law. The current through a resistor is proportional to the potential difference across the resistor. So if y was the current through the resistor and x was the potential difference across the resistor, we would have a linear relationship between these two. The current would be 1 over the resistance, a constant, times the potential difference across the resistor, our other variable x. Let's have a look at some other functions, just to try and get absolutely clear what this definition of linearity implies. Okay, we have a series of 5 functions here. Which ones of them are linear? Pause the video now and have a think about it. And when you've got your answer, start the video up again and we'll go through them. Okay, we'll start with the first one. Is this linear? Well, y equals 6x plus 2. If I was to plot that on a set of axes, where this is y and this is x, then what I would get would be something that would look like this. It is a straight line, but it's not the definition of linearity that we're using here because the straight line doesn't go through the origin. And working with this definition of linearity, we need the straight line to go through the origin. So number 1, no, it is not linear within the definition of linearity that we're using here. Number 2, I could write that as y equals 8x. Yes, that's linear. A graph of that would go through the origin. When x is 0, y is 0, and it's a straight line. So number 2, yes, that is linear. Number 3, y equals 3x squared. A plot of that graph would look something like this. No. Definitely not linear, it's not a straight line. Number 4, y equals 1 plus x squared minus 1 minus x all squared. Okay, it's a bit of a trick. The answer is yes, it is linear. But to see this, you have to do a bit of algebra. 1 plus x squared minus 1 minus 2x plus x squared. That would give you 1 plus x squared minus 1 plus 2x minus x squared. The constant terms 1 cancel, the x squareds cancel. We're just left with y equals 2x. Yes, it is linear. Yeah, sorry. Finally, 5, y equals x plus 2x. Very similar to number 2, we would end up with y equals 3x. So yes, the input x times a constant gives me the output. Number 5 is linear. So the correct answer, 2, 4 and 5 are linear. Now the inputs and the outputs don't have to be unchanging. They can be functions of time. This function, for example, we have the output y of t is equal to 2 times the input at time t plus 3. That's an interesting function. Why is it interesting in particular? Well, it's impossible to build. We call functions like this acausal. Consider what happens at time t equals 0. Y at time t equals 0 is equal to 2x at time, well, if t is 0, that would be 2x at time 3. That is the input at time 3 seconds. This is the output at time 0 seconds. So the output is proportional to the value of the input 3 seconds in the future at time 3. That's impossible. So if you ever see an expression like this, something is very strange with the circuit that has produced it. Something much more reasonable would look like this. And we see that type of relationship very common. This would mean that y at time 0 would be twice the value of x at time minus 3 seconds ago. So there's plenty of time for the system to take the input, multiply it by 2 and deliver it to the output. Despite the fact that circuits with characteristics defined by this sort of equation cannot possibly exist in real life, all of the mathematics that we're about to do for linearity and superposition would work with them just fine. But I won't be using any of them as real examples. Okay, hopefully everyone has a good idea of what I mean by linearity by now. In the next video, I'm going to extend this definition to systems which have multiple inputs.